Hello, I'm Silent Death, and welcome to the 6th episode of the comprehensive Ferram Aerospace Research tutorial. In this episode, we will be covering the FAR graph, how you can combine the information from the FAR graph with the information from the stability derivative page to help design your plane, what information you should be getting from those two screens, and how to use that information for placing flaps and spoilers. The FAR graph is much more frequently discussed, less scary than the stability derivatives, and much easier to understand, which is probably why it is more frequently discussed. Let's give you a general overview. It has two methods: sweep angle of attack and sweep Mach. Again, angle of attack is the difference between the direction your nose is pointing and the direction your plane is going. The difference between where you're pointing and the prograde marker on the nav ball as it relates to pitch. So how far you are pitched from your prograde marker. Here we can enter either a Mach number or angle of attack, and then we sweep the other value, and it goes from the lower to the upper divided by this many points. So if we press sweep angle of attack, it would say Mach 2 from angle of attack of -20 to +25. We could do the same thing by sweeping the Mach. We said an angle of attack of 10 from Mach 0 to Mach 6. And I did that wrong. That way. So this tells us some things about our craft if we're holding at a 10-degree angle of attack. Generally, we use a sweep angle of attack and only occasionally use sweep Mach. Now let's go over what all these lines mean. The red line is the coefficient of drag. The light blue line, cyan line, is the coefficient of lift. These two are not the absolute drag or lift values, merely the coefficients. The green line is lift divided by drag, a measure of how efficient your craft is at that particular pitch angle, or Mach number if you're doing a sweep Mach. The yellow line is, according to the help file, the sum of all the forces that cause your nose to pitch up or down. What that actually means is if this line is below the axis here, your nose is going to want to pitch down from this angle of attack. If it is above this axis, your nose is going to want to pitch up from this angle of attack. What we want is, if we have a positive angle of attack, we want it to be pushing us downward. That way we'll go back towards neutral. And if we have a negative angle of attack, we want it to be above the line, so that it will again push us back towards neutral, or push us back towards 0. If it was above the line in the positive angle of attack, that would mean we would continue pitching up further and further and further until we started backflipping. The point where it crosses the axis is the neutral moment, where the forces pitching your nose up and pitching your nose down equalize. And this is what value your nose is going to want to maintain without any input from the controls. So if we were flying at a Mach 2, we did not touch the controls, it will naturally settle to about -3 or 4 angle of attack. If the line splits like it does right here, that means we stall at this angle of attack and this speed. The line is the values after the stall, the little kind of faded line. How we use that is if we go to the data stability page, pick that speed and whatever altitude we're going to be traveling at that speed at, see what angle of attack we need for level flight. If that angle of attack is higher than when the stall occurs, which in this case it is, the stall is occurring at about an angle of attack of 5 degrees, that means that we cannot achieve level flight at that speed. We can only fall down, basically. Or, another way of saying it is we would not be able to take off at that speed. So what would our, let's say 2.5 maybe? See our minimum takeoff speed? About 85 meters per second. We can maybe just take off. If the angle of attack reads 0 degrees, that means a level flight is not possible. You can use the same method, finding out your angle of attack, at higher altitudes and higher speeds, to see if your plane will be as stable at that altitude. In this case, no stall issues at all. We not only need to check if we stall at a particular speed and altitude, we need to check if we can actually reach this angle of attack needed for level flight. So at altitude of 30 kilometers and a Mach number of 3.5, we require an angle of attack of 18.2 degrees to maintain a level flight. If we look at our thing, we have this pitch setting, which is a percentage. So that's 0%, and 1 is 100%. If we sweep angle of attack, sometimes we have to do it twice to make sure it updates. You'll see that our angle of attack, or our pitching moment, looks like it's a little bit below 18 degrees. If we zoom in a little bit, we'll go 15, 20. Yeah, so it is definitely below 18 degrees. That means we will not be able to achieve a level flight at this altitude and this speed because we cannot pitch up this high, even with full input from our controls. Another way we can use the FAR graph is for setting up our flaps and spoilers. If, for instance, we want this plane here to have a cruising altitude of 25 kilometers at Mach 4, it needs an angle of attack of 6.65 degrees to hold a level flight. And as you recall, our pitching moment, neutral pitching moment, is down -3 or -4 degrees. So what we can do is we can add some flaps and try to move our neutral pitching moment up to about 6 degrees. So we will turn off pitch here, turn on a pitch for this one. And activate flaps. Spin mode attack. And you can see that increased our drag. Our flaps are actually going in the wrong direction. Put them right there. And that did not really help us out. Mostly because if you look at our center of mass, these do not have a very much leverage. We'll just turn off flaps for those so we get back where it needs to go. And then we'll try flaps on the rear horizontal stabilizers. Turn off. Well, I guess we'll leave pitch on. Activate flaps. And you can see that moved us up quite a bit. We could increase these a little bit more. And now we're way up. So by tweaking these, we can basically move our neutral pitch moment to exactly where we want it. And that way we can fly straight and level. Or well, we won't lose altitude without even touching the controls. A pretty useful thing. Another way you can use this is for setting your climbing pitch at your most efficient lift to drag ratio. So for instance, about Mach 1 is where we'll be climbing from 10 to 20 kilometers ish. So we'd want a pitch somewhere around in here, a neutral pitch. Activate flaps, set level 3, maybe a little bit more pitch there. And as you can see, as we're increasing our flap pitch, we are increasing our drag and decreasing our efficiency slightly. So right about here at full flaps, we would have the most efficient lift to drag ratio. And that would be a good angle to be climbing up, because we would accelerate the fastest. You can tweak your various flap settings so that, for instance, you have one flap setting for cruising at Mach 4, one for climbing at Mach 1, and another for, I don't know, a landing or taking off. I guess we can look at a landing and taking off. As we saw before, we need an angle of attack of 7.3 degrees at an altitude of 0 kilometers to land or take off. If we set our flaps as they're already configured to the takeoff setting, we increase our pitch moment a little bit forward, but still not quite enough for level flight. If we go all the way up to 3, then we're stalling now about 9 degrees, so we would be able to take off at this flight. However, we would try to pitch up until we stalled if we did so. So we would be kind of fighting the controls if we did that. Probably still possible because the degree of a push up is not very high at the angle we would need to be. And we would also be kind of teetering on the edge of a stall. So it's something that would be a little bit iffy. But if you had a very heavy cargo plane that didn't have a very good thrust to weight ratio, you could just barely get it to Mach 0.2 at the end of the runway, then adding a little bit of flaps would help you out there. You can set up your flaps and spoolers from this screen in the sort of Space Center overview thing. You set your hotkeys here. Note that even if you don't yet have action groups, or the specific action group for these, unlocked by upgrading your VAB or space plane hangar, you will still have your flaps placed in those action groups and they will still function, even if you have not yet unlocked the upgrade for that. So they are automatically placed without you having to have the upgrade. You can also toggle a few other things, like aerodynamic failures, and display the forces, coefficients, and shielding when you right-click on a part while you're flying. Of course, I generally prefer to use the flight tent thing for that, but you can use these if you wish. And there's a few other options here, which is a little bit beyond the scope of this tutorial. If you are having a difficulty getting the pitch moment to move when you adjust your flaps, you may need to upgrade to the latest dev version of Ferram Aerospace. Some mods seem to be conflicting, or there seems to be some bugs in the Ferram Aerospace where it is not updating properly. If you have the latest dev version, you should have this little screen here at the time of this recording. To download the dev version, you need to go to the Ferram Aerospace GitHub page and click on Download Zip right below the Clone to Desktop button, which will download not just the mod itself, but all the source code for the mod. You are only interested in the game data folder in that zip file, which you install as you normally would. By default, Ferram Aerospace will place all of your flap deflections in the same action groups. So all the increase are in group 9, and all the decrease are in group 10. If we wanted to have flaps increment, like for instance on the canards increment differently from the flaps on the tail section, we would have to manually change that here. Of course, that is only an option if you have upgraded the spaceplane hangar enough to be able to set up custom action groups. Now let's talk about spoolers. They are generally used in one of two ways. One is to hold you onto the ground when you are landing. For instance, if your landing gear of your plane was set so that it was either level or pitched upwards, you'll have a difficulty staying on the ground when you land. So you may have a spooler set to help make sure that your nose stays firmly planted on the ground. The increased drag will also help slow you down. Another thing people do is set up a pair of spoolers in opposite directions to kind of act as a poor man's air brakes. The downside of this is, of course, that now we cannot use these two control surfaces because they've been taken over by the spoilers. Generally, it is easier just to have some air brakes. Also note that the deflection used by spoilers is shared with the deflection used by flaps. So if you have both spoilers and a flap set on a part, you kind of get a weird behavior. It basically means that you should not have flaps and spoilers active on the same part. There is no way, for instance, to have these go downward on spoilers but upwards on flaps. At least not in this version of Ferram Aerospace. Another thing you may wish to do is adjust the slope of the yellow line. For instance, if we take our tail section and we tell it to pitch that way with a negative angle of attack, and we make our nose, or canards, pitch up, so what happens is, say we're at 6 degrees, these will be pitched up at 6 degrees, these will be pitched up 6 degrees. Any control input will be from this position they are at now. And if we look at our line, you can see the slope is greatly decreased. If we actually go out a little bit, you'll see that continues up till we almost get to a neutrally stable point at 18 or 19 degrees. This can be desirable in some situations. It can improve your stability, but in other situations it can cause problems, usually by messing with these values. It is just something that may give you a little bit more control without making your plane too maneuverable. For instance, if I wanted this to have the full range of up to a 40-degree angle of attack, then I could drop the pitch down to, say, 25%. And that would let me pitch this up to 10 degrees from the angle of attack. That is it for this episode. In the next episode, we will begin doing some case studies, designing some craft on camera so that you can see the various concepts discussed previously in this tutorial series in action. If you have any questions about what was covered in this tutorial, feel free to leave a comment below, and I will do my best to answer them. Like if you like, subscribe if you're not. Thanks for watching, and I will see you next time!